So bone growth can only grow via the process of appositional growth. You can only put new bone on top of either older bone or cartilage. Like I said, bone can't grow from nothing. Bone has to actually come and have a template that it can follow. Come in and have a template. So, long bones and bony projections increase in length because of growth at the epiphyseal plate. This little dude right here that I showed you earlier. These separate the diaphysis from the epiphyseus. Growth at the epiphyseal plate involves the formation of new cartilage by interstitial, in between tissue growth, followed by appositional, on top of old bone or cartilage growth, bone growth, on the surface of older cartilage. So do you see this square right here? I'm going to blow that up so that you can actually see these cells. So in this picture here, of course I did that, and I don't know what I just did. In this picture here, again, in this picture here, I've got a zone of resting cartilage, a zone of proliferation, a zone of hypertrophy, a zone of calcification, and ossified bones. So, drawing what this is, going back to this picture here, see that little square? That's what I'm showing you. So the epiphyseus is up here. You've got the end of the bone up here with the cartilage cap, and then the diaphysis, the shaft of the bone, is down here at the bottom. Okay? Just to kind of let you know where I am, where this is. All right. The zone of resting cartilage. The zone of resting cartilage up here is basically the cartilage that attaches the tip of our bone, the epiphyseus, to the rest of the bone. It's an anchor point. Then we have the zone of proliferation. If you look, you can see little cells inside of this space here, okay? This is where the cartilage is being produced. On the epiphyseal side of the plate, the chondrocytes divide, and it's kind of like having a conveyor belt, like your skin. As they divide, they push this up further, making my bone longer, okay? The zone of hypertrophy. Remember, hypertrophy is just a real fancy way of saying they swell up. So if you look at the chondrocytes in section 2, they look real small. But if you look at them in section 3, all of a sudden they've become these big, huge things. You can actually see the individual bubbles. You can see them here versus up here where they're real tiny. That is actually making room for the bone to come in. The next section is the zone of calcification. So remember what I said about cartilage cells. Cartilage cells depend on diffusion to get things into and out of those cells, to get them fed, to get waste products out. If I calcify the matrix, if I turn that matrix into something solid, then they start to die. And you can actually see that here. If you look here, those cells look really, really sickly. And eventually you'll notice that there are no cells in these spaces anymore because they've died, they've gone away. Now, the fifth region is where the ossified bone comes in. Remember what I said about bone. It has to grow on the surface of something else, or it has to have a template. Well, this calcified zone is going to be the template. This bone down here is coming in and basically replacing it. So if you think about stacking books, let's say, on top of each other, I'm growing calcium, hypertrophying or making them enlarged, letting them die, and then replacing it with bone. If you do this on both ends of your bone, so I'm going to change colors again. If you do this at the end where you've got cartilage and you replace it with bone, You've got cartilage and you replace it with bone. And this end down here, you've got cartilage and you replace it with bone. You've got cartilage and you replace it with bone. Eventually, your bone grows in length. Now, the articular cartilage, you have to remember something. If I've got a bone as a kid and it's this big, and I keep growing it in length, I'm going to have a really, really small end to this bone. That doesn't work. So you know how we have the bone and then we've got the cartilage cap on top? What we just did in that growth plate in this part of the bone here, we're going to do the same thing here. And what that does is, as our bone grows in length, it basically helps to make this bigger so that it compensates for the fact that we are getting bigger. It's very similar to the epiphyseal plate growth. The only difference is at the end of this growth, when we become adults, when we become mature, we still have cartilage on the ends of our bones so that our bones move more smoothly. Now, oppositional growth. I'm going to go back for a second. I want to show you something again to remind you of something. So when we talked about the periosteum, I pointed out all of these blood vessels here on this outer lining, right? That's going to become important here, because if you think about how wide your bones were as a baby, they were probably about the width of your pinky. Now imagine having a bone as long as your femur, the width of a pinky. That would pretty much break really, really quickly. So we not only have to worry about growing our bone in length this way, we have to worry about growing our bone in width out this way. Okay? So how do we do that? All of those blood vessels I just showed you. The process of appositional growth. Remember, appositional means I'm growing on the surface of older cartilage or older bone. Well, if I surround those blood vessels with bone and create osteons around the entire circumference of that bone, that's going to actually make my bone wider. So I actually do grow my bone in width, in length, and the epiphyseus, the two ends of the bone, so that it compensates for the fact that my body gets bigger. So the factors affecting bone growth, there are two things: nutrition and hormones. Technically, the day you were born, your genetics dictated that you would be a certain height and your bones would grow to a certain length. If everything is perfect, your hormones are great, your nutrition is great, then you will reach that potential height. But if not, you won't. So let's explain that. Bone growth requires two things: new cells and new matrix. I've got to build new bone. There's no way for me not to do that. Well, if I want to do that, I have to have sufficient nutrition. I've got to have the source of materials, and I've got to have enough nutrients to make new cells. If you don't, then that can't happen. If you're going through a period of starvation, your bones will start to grow at a slower rate, okay? Especially if you're in severe nutritional deprivation. In other words, you're not eating like you should be eating. It can lead to somebody not reaching their predetermined height, their genetic height. Remember, I told you it's already programmed into your genetics. Vitamin D is actually required for calcium absorption. Without it, you get a disease called rickets. Basically, your bones are bendy. Your weight will cause your bones to bow. This actually was a real bad issue during the Depression. During the Depression, you have to remember, I didn't have enough money to feed my family, much less a cow that I could get milk from, or a goat that I could get milk from. So they were without calcium for a very long time, and their bones began to bend, almost like pipe cleaners. They just didn't have enough concrete in those bones. They had a lot of rebar, but they didn't have a lot of concrete, so they just bowed over. Another thing that we need is vitamin C. Vitamin C is required for the rebar part of our bones. It's what gives us our flexibility. When we don't have it, we develop a disease called scurvy. If you've ever seen anything about scurvy, basically you end up losing your teeth because collagen is a major portion of our ligaments that hold our bones together, including our teeth in our mouth. And when you don't have enough collagen, you actually can't develop those ligaments and your teeth fall out. When it comes to bones, though, if you don't have enough vitamin C, your bones become very brittle and they'll break. If you look at the x-ray, you can see these darker lines in the x-ray here. These are time frames when this person's bones didn't grow properly because they were in severe nutritional deprivation. In other words, they were starving during those times. Now, hormones. You've got hormones like growth hormone, thyroid hormone, estrogen, testosterone. These stimulate growth. Deficiency results in a decrease in size for an individual. One of the reasons that you go in for checkups is because they're actually checking your hormone levels. And if your hormone levels aren't right, they will actually supplement. They'll give you pills or something to take to basically try and get you back on the right track as far as hormone levels. Something with estrogen and testosterone that's also kind of interesting is that initially they do give you growth spurts, but as you get older and those levels go up higher and higher and higher, that means you're reaching maturity. You're reaching a sexually mature age where you are capable of having offspring, which means that you don't need to grow anymore. So when you reach that level of estrogen and testosterone, it actually seals the growth plates and turns them into the growth lines. If for some reason you've got really high estrogen or testosterone levels as a female or a male respectively, you'll actually stop growing early because it'll solidify those plates. Bone remodeling. Remodeling converts woven bone into lamellar bone and allows bone to change shape, adjust to stress, repair itself, and regulate body calcium levels. Pretty much, if we need to, we can rearrange your bone fibers to deal with extra weight, less weight, etc., etc. For somebody who is bedridden, they actually lose bone density because the normal pressure that's being put on bones as you stand isn't there. I already talked about that. So bone repair. There are 4 steps to bone repair: hematoma formation, callus formation, callus ossification, and bone remodeling. So let's talk about those major steps. In hematoma formation, hematoma is a very fancy way of saying bruise. You fracture your bone. Remember, you've got all those central canals that are actually blood vessels and your perforating canals. You just ruptured those things. That means that you're going to have blood leaking out. That's the hematoma. It's a bruise. The fracture will cause damage to the blood vessels. They'll break. They'll begin to leak, causing the formation of a hematoma, a bruise. The damage also leads to a lack of blood flow. Literally, I've cut off the blood flow to these little ends of my bones here. Let's see. Causing damage to the tissue or the damaged tissue to die. This hematoma will also form a fibrous clot to stop bleeding. Now, the callus formation. Several days after the fracture, the blood vessels will start to grow. You can see them growing here. As the clot dissolves, macrophages will begin to clean up the cell debris. Osteoclasts will begin dissolving the dead bone tissue. So see this kind of lavender? This is cartilage. Remember I told you cartilage has to be put down first. I've got some woven bone in here. Remember, woven bone is like a rough draft. The chondroblasts will begin to form cartilage among the fibers being produced, and osteoblasts will also begin to form bone tissue. These help form the callus. This kind of semi-hard cartilage is actually going to act kind of like a splint. It's going to help this bone be a little bit more stable and stabilize the break. Now, the callus ossification, just like what we saw in our epiphyseal plate, the cartilage that was there starts to ossify. It starts to become hard, basically leaving behind a template. We've got an internal callus and an external callus. You can see that this still doesn't look normal. I don't have a diaphysis here. I don't have compact bone here. I don't have a smooth surface out here yet, although I do have the periosteum back in place. I have a lot of remodeling to do to make this look normal. You'll also notice that the bone at the ends here is kind of dark. That's because it's dead. Remember, I cut off the blood supply. So I've got to clean all of this up. So much like in fetal development, the cartilage from both the internal and external callus is replaced by woven bone. This further stabilizes the break. Let's face it, cartilage is pretty bendy, but now that I've got woven bone, it's even better splinted. It's actually holding better. Finally, I've got the bone remodeling. Repair is not complete until the lamellar bone replaces all of the woven bone. I've got the compact bone. I've got the central sorry. Bone remodeling. Repair isn't complete until the lamellar bone replaces all of the woven bone, compact bone along the outside, spongy bone internally. The repaired zone usually remains slightly thicker than the adjacent. If it occurs in the diaphysis, the medullary cavity also has to be restored. So if you look at the bone remodeling, I've got compact bone here. I've got a medullary cavity. I've got spongy bone along the lining here, and I've got blood vessels. Now, you'll still see that there's kind of a thickening around where that break happened. And honestly, if you look at an x-ray, it looks slightly thicker here. And to be honest, if you break anything again, you probably would break up here and down here, but not in the same place because it is slightly more dense than it used to be. So talking about different types of fractures, you've got green stick fracture. Green stick fracture is an incomplete fracture. Happens a lot with kids. Kids' bones tend to be more flexible because they're designed that way. Kids are clumsy. So if you think about a rose stem, if you try to break a rose stem just by bending it, it splinters more than it actually breaks. That's kind of what a green stick fracture is. In kids, when you see green stick fractures, you know that there was really a lot of effort put into that break because kids, like I said, are a lot, well, they're flexible. If a mom comes in with a story that doesn't match up to that green stick fracture and how it could have happened, a lot of times CPS is called. A spiral fracture. A spiral fracture happens when you break because you're spinning. So the best way that I can think to describe it, imagine somebody holding on to a roof and they're hanging and their body starts to spin, but they keep on hanging onto that roof. It breaks along that spiral. Again, this is one of those that if the story doesn't match up, you usually have CPS called because the story doesn't match the break. If you've got a kid who says they fell off their bike and they've got a spiral fracture, that doesn't make any sense. A comminuted fracture is a crush injury. Usually with a comminuted fracture, you're going to have to put plates in place to hold the bone long enough for it to grow back together. Transverse is pretty simple. It's a break across the bone. You usually get a cast and you're good to go. Compound fracture. That means that the bone is displaced. It is not sitting in the right place. And usually it also means that you're going to have surgery to put it back in place. Those movies where you see a compound fracture and they just kind of pull and push and put it back together, yeah, it doesn't work that way. Because this has been exposed to air, you've got to do all kinds of cleaning and debriding, and all kinds of issues are going to happen if you try to put this back where it was. A compression fracture basically is like crushing a tin can. You've got this happening in the vertebra mostly, and it's when the vertebra kind of smush down. Very painful. A tibial stress fracture is also called a hairline fracture. Well, a stress fracture is also called a hairline fracture. The example is tibial, but it can happen anywhere. And you got to remember that we have our nerves running on the outside of our bone. So this is painful. This is just as painful as anything else. Calcium homeostasis. Calcium has to be maintained within narrow limits for functions such as muscle contraction and maintenance of membrane potentials. Because bone is a major storage site for calcium, it can be used to maintain homeostatic blood calcium levels. If levels are low, the osteoclasts will basically break bone down to put calcium back in the blood. When it's too high, the blast will build bone matrix, take the calcium out of the blood, and put it into the bone. Basically, we have to have a good amount of calcium, a correct level of calcium in our blood. If we don't, things don't work. We have two hormones that help with this. Parathyroid hormone, PTH is parathyroid hormone, and calcitonin. So you can read all this if you want to, but this is pretty much what it says. Calcitonin decreases blood calcium by basically decreasing bone breakdown. So if I've already got enough calcium in my blood, it tells the osteoclasts, the ones that crush or break down bone, to stop. Just stop doing what you're doing. We've got enough. You're good to go. Parathyroid hormone, however, is the exact opposite. It increases blood calcium levels by increasing bone breakdown, calcium absorption from the small intestine, and calcium reabsorption from the urine. So we've got calcium going into our blood from the bone, from our food. We bring it in from the intestine. And when we make urine, instead of letting it go out in the urine, we actually pull it back. So parathyroid hormone increases blood calcium levels. Calcitonin decreases blood calcium levels. The effects of aging. With aging, the bone matrix is lost and matrix becomes more brittle. Cancellous bone loss results in thinning and loss of the trabeculae, the solid parts of our spongy bone. Compact bone loss mainly occurs from the inner surface of the bones and involves less osteon formation. Loss of bone increases the risk of fractures. It can cause deformities, loss of height, pain, stiffness, and loss of teeth. Everything goes downhill as we age. With aging, the bone matrix is lost. Literally, we are starting to lose bone mass. I'm sure you've heard of osteoporosis, and that's when this loss of bone is devastating. We don't have enough, and we're losing it as it is. With osteoporosis, our osteoclasts are staying really, really active, and our osteoblasts aren't doing their job. So there isn't balance between them. We're breaking down more than we're making. With this comes the fact that our bones become brittle as we get older. So that is the end of chapter 6.